Today talks are mostly dedicated to 21 centimeter observation and experiment. Okay. So the first talk is by Samir Choudhuri, who will summarize the current status of 21 centimeter observations.
So thank you, organizer, for inviting me. And yeah, so mainly I will be talking about the current status of cosmological 21 centimeter observation. And the background image is one of the sensitive, largest radio telescopes in India, is the MRT. I'll talk about that. So in this talk, mainly we will focus on the few questions that we want to ask. Why do we need observation? And if we want to do observation, what we actually want to observe, and if the quantity is fixed, how to observe them in our current experimental setup, and using this setup, what is the current status? So these are the main broad questions we are planning to answer in this talk. So why do we need observations? So this is two different reionization model based on different physical, astrophysical and cosmological parameters. And from this plot or from this image, you can see that the reionization history is changing depending on the parameters. And this is image is taken from this web page. But we don't know which one is the correct. So to constrain and also to fire to make a decision on that reionization history or to constrain the reionization parameter, we need observation. So that is the now question is what we want to observe. What is the observable that we are planning to observe and what is the progress? So mainly in radius, mainly in 21 centimeter observations, we plan to measure the brightness temperature fluctuation. And this is the H1 cloud, and this is the background radiation CMB, and the CMB radiation is passing through this gas, and there is a fluctuation in the brightness temperature, and this is the expression. So the quantity that we are planning, that we want to measure, is the brightness temperature fluctuations due to the neutral hydrogen in the intergalactic medium. Okay, so now we know what we want to measure. So how and what is the behavior of that? So actually, what to observe? So this 21 centimeter fluctuations can be observed in both ways. One is the mean temperature, mean all sky global signal. This is the this is the pattern or the plot of this brightness temperature fluctuations, and the upper panel is the fluctuation. If you concentrate a particular patch of the sky, you can see the fluctuation. So this is the two quantities of the brightness temperature we are interested in, and I think yeah, there are many observational setup they are trying to measure. This is the age. I am not going to repeat. I think this is the most hard word in the ages in this talk. So I am not going to repeat that. So there is another experiment, SARS-2 in India. They are also planning to measure the global signal, and they, based on their observation, they ruled out some models of the global signal. Later, they improved their experimental setup and they put it in the water. And in this new observation, what they actually uh, this observation of the edges, they did not get any signal. So they have the observed brightness temperature fluctuations, and they, in that brightness temperature global signal, and from this signal they try to find if there are any global signal present or not. And this is the parameter of that S factor. If it is S is 1, that means the edges signal is there. If it is not, that means no edges signal. And they, from the observed data, they fit, and this is the plot of that factor S. And it is mostly 0 with mean 0 with some standard deviation. So they claim that this is not, the edges signal is not present in their data. This is another experiment. This is proposed. This is the REACH, radio experiment in analysis. So this is all of the global signal that I talked about. So I'll talk about the fluctuations later. And in this experiment, this is slightly different compared to the others. Here it is two antennas simultaneously measuring the sky signal to reduce the systematics if they are present. So one is hexagonal shape, that is the dipole antenna, 50 to 130 megahertz, and there is a conical shape log spiral antenna, and this is the another frequency band. And from this experimental setup, they will observe the sky at simultaneously at two different observing bands using two different instrumental setups, so that instrumental systematic can be reduced. And using this, they showed that. So this is for log spiral one antenna. This is the hexagonal dipole. If you combine these both signals, this is a simulated result. Still, the data will come and they will publish later. But from the simulations, that you can constrain the reionization history more actually using this simultaneous measurement. So this is another experiment. This is another proposed experiment, PRISM, and it is located in the Marian Island in sub-Antarctic. And this is the location, and the advantage is that if you see the RFI plot, it is very less compared to the other. So this is the RFI, this is the signal as compared to the Marian Island. And here, this vertical lines is the RFI. And this is the black is from the Karoo Desert in South Africa, but this red line is from this island. So just to reduce the RFI signal, it is located, they put it in the Antarctica region, and the RFI is very less. Okay, there's another experiment, global signal. So I'm just summarizing all the experiments, what the people in different parts of the globe, they are working and taking the data and giving some result for the 21 centimeter global signal. This is another experiment, LEDA, and this is the Waynes Valley Radio Observatory in California, and this is their result published in 2016. And from that, they put some upper limit of the amplitude. This is still a noise dominated, no absorption feature, but they put some upper limit on that. So this is another experiment. Okay, there are some sky-based. This is the some lunar-based observatory. So these are this plot, this table summarizes all the current experiments for the global signal that are available and that are working now. So AJ, SARAS, LEDA, PRISM, all these things, and what is the frequency band they are working, and what type of antennas they are, and what is the current result. All these things are summarized in this table in this paper actually. And this is the REACH experiment that is slightly different compared to the others. Here, two antennas are present simultaneously, and this is more accurate, they claim, but still we have to wait for the actual result. Okay, so this is the global signal. Now, as I showed earlier, we can measure the 21 centimeter in fluctuations. For the fluctuations, the instrumental setup is slightly different. We are concentrated on a particular patch of the sky, and we will measure the fluctuations from that. So the experimental setup is radio interferometer, not the dipole or the single dish telescope. So in the dipole, this is one schematic diagram. Suppose two antennas are present and the electric voltage is coming, and then finally we will correlate these two antennas, and what we will give is called the visibility. So that is the observable from the radio interferometer. And this is basically, if you see, so there are some primary beam patterns. So sky pattern is there, and also the primary beam pattern, that is the antenna response. So if the antenna is pointing toward the up, so it will be more response. The response function will be more towards that direction, but it will be less if you go beyond this head center. But there are some instrumental noise also. What the radio interferometer actually measures, suppose this is the three antennas. What actually it measures? The Fourier component of the sky fluctuation. So any fluctuation in the sky, we can decompose it in different Fourier modes, and small separation of the antennas will measure the larger Fourier modes, and the large antenna separation will measure the smaller Fourier modes. So if we combine all of them, we can reproduce the fluctuations in the sky distribution. So that is the radio interferometer, what is actually measured. So when we have the visibility that I showed in earlier, the correlation, now we have all possible combinations of the antennas. Here it is 2, but if it is an n number of antennas, we will get n-C2 combination. Now if we combine all of them, we will measure the fluctuations in the sky distribution. So that is the observable, but it is still, we can't say anything about the 21 centimeter from this. So we have to give some sensible result or sensible quantity so that we can compare this with our understanding of the 21 centimeter. So that is the formalism we are using, two visibility correlation. So two visibilities means one pair will give one visibility, another pair will give another visibility. Now, if we combine these two different Fourier modes, what we will get as the power spectrum. So this is the quantity we are interested, and we can correlate this quantity with the prediction of the 21 centimeter physics or 21 centimeter underlying 21 centimeter physics. So we have to correlate them. So this is the formalism, two visibility correlation, and we have to normalize with proper factor because the instrument has some response that I call primary beam, and also there are some noise in this. So this is itself a, I will talk about that. This is itself a huge work because this, by getting the visibility data only, we can't measure the 21 centimeter signal or the power spectrum. Lot of work we have to do that. So for the fluctuations I talked, okay, we have radio interferometers. It will give some quantity. By correlating to different Fourier modes or different pair of antennas, we can measure the 21 centimeter signal in principle in the power spectrum. But there are a lot of challenges. So one challenge is foreground. So we have talked a lot of things about this. So galactic foreground, extra galactic foreground, RFI, all these things are there. And as this is the noise so itself, because the cosmological 21 centimeter signal is very faint. Noise, if you do the Fourier transform, inverse Fourier transform, you have the data. So image plane is not possible. You will get only the noise, no signal. As I showed, the RFI is another thing. If something is present in the RFI, basically radio frequency, you have to remove this part because this is not the signal. This is from the RFI. So we have to remove. So some signal or some information is missing in this channel. So RFI is one of the problem, and that will create another problem. And I'll talk about that. So this should be less to reduce that. Another is the calibration issue. So again, this is another observational technique. So the radio instrument is not perfectly. It will not give the result from the sky only. There are a lot of things. One I said noise, and another is primary beam. But the instrumental gain is there. When the signal is passing through the electronics, it will introduce some gain. So that we have to correct. For the 21 centimeter signal, so we have to calibrate this signal with respect to some calibrator. But this process should be accurate enough so that 21 centimeter signal can be detected. So this is one of the plots where the calibration error presented, what should be the calibration error, and this is the noise level, and this is this line green shows that how much accuracy you need for this calibration process. So if you see that this is the 21 centimeter signal and this is the noise. So if the calibration is high enough, you will see the calibration error. You will not able to see any signal. So your calibration error should be less enough. This is 10% means 0.1%. So this is another challenge. You can't, your calibration process or calibration steps should be accurate enough so that. So I am talking about the challenges that we are facing from the 21 centimeter observation or from the data. So this before say something about the physics or 21 centimeter, these challenges we have to tackle, we have to overcome, then we can say something. Another challenge is the modeling incompleteness. What is this? As I said, the calibration process, you need some sky reference. Okay, this is the sky and I am calibrating based on that, and whatever the unknown signal I can predict from that. This is, suppose you're depending on your instrument response, you can't measure all the source in the sky. So there are some limitations depending on the instrument. So this incompleteness will affect our measurement. So this is one of the plot, just simulated plot. Here you can see that due to the incompleteness, if the incompleteness is much more, for the MWA, so this is the 21 centimeter signal at 10 times and 20 times. So if it is very less, these 3 lines, that means you can measure the signal. For the MWA, if the model, so there is some one, they took the model greater than some flux value, that is the Jansky, I think 100 millijansky. So for this case MW, these all lines are above this panel. So that means if this error, if the model incomplete, so your model should be complete enough so that these lines goes below this line, so that you can measure the 21 centimeter. For the loafer, it is quite optimistic. So you can measure some part from this part, but still you have your model should be complete enough. So this is another challenge. When you are calibrating something, your model should be enough, should be complete to measure the 21 centimeters. Another challenge is ionosphere. So this is one of the plot that shows the sky image at different. So this is the ionospheric calibration they did. So just if we focus on the left panel, due to the ionospheric fluctuations, your sky image should be not good enough. So we have to correct them. So there is this direction dependent calibration they apply at different level in interactive process, and finally you can see that. So ionosphere fluctuations is there and you have to correct them. So this is another challenge. Another challenge is the mutual coupling. What is this? So as I said, there are 2 antennas, the signal is coming and we are correlating them. But still, if the antennas are located at 2 nearby position, they will couple each other. So one signal coming here can go to in these antennas also, and vice versa. Also, this is the self interaction. So if the electronics is there, some part of the signal will go back to the antenna and come back. So this kind of coupling may happen and it will affect our measurement. So this is one of the simulated results of the coupling. So there are 2 coefficients that shows the coupling between 2 different antennas. And in principle, if there is a no coupling, it should be a noise line. But you can see that there are some peaks depending, because some parts of the signal, this is the delay, how much time is taking from, and at particular delay, this is the high signal. That means some coupling is there between these radio interferometers. So and also it depends on the location and also the signal strength. So it is difficult to remove, but you have to remove them. So if the antenna is quite nearby, this is another challenge. So what I talked, the radio interferometers can be used to measure the 21 centimeter fluctuations, but there are lot of challenges that I talked about: noise, foreground, mutual coupling, all these things. But there are some hope also. This is the foreground image, foreground spectra, and it behaves smoothly. So one of the, now I am talking about the how we can overcome these challenges to get something from the data. So this is the plot spectra of the foreground as a function of frequency. But what you see that their foreground is behave smoothly as a function of frequency. So any smooth component can be removed to reduce the foreground, because this is the most dominating in our data, which we don't want. So we have to remove them, and finally we will get the signal plus noise. Noise can be reduced by more data volume. Anyway, so this is one of the hopes that we can apply, but there are some other problems also. Anyway, this is the foreground removal technique. This is another technique is called the foreground avoidance. So this is the solution. So any smooth component along the frequency will reside. So this is one space K parallel K perpendicular, and any smooth component will reside in this wedge shape region. Whatever is above this will be foreground free. So we can just remove this part. We don't want to consider this part to avoid the foreground, and whatever is extra space available, we can measure the 21 centimeter. So this is the avoidance technique. So these are the few possible solutions. So for example, the mutual coupling, you can model something. So there are some models that we can use to remove the foreground, some systematics, and get some results. So these are some of the results that are currently available. This is the GMRT 30 antennas in a Y shape in Pune, and this is the first result. One of this is not, this is the multi-purpose you can use for any radio observations, but they have used this paper. They have used this GMRT for the 21 centimeter UR power spectrum, and here you can see that result. This is the one of the early results in 2013, and you can see there are some upper limit, but still this is not that much accurate to say something. This is another radio telescope. So these are the radio telescopes which operate in interferometric mode to measure the fluctuations, not the global signal. So this is the MW, Murchison Wildfield Array in the Australia, and this is the tile shape. And here it is 256 element, and this is the frequency band. And they use the hybrid approach. Foreground removal some part and foreground avoidance some part, and then finally they give the upper limit. So these two plots shows the upper limit from this paper, and this is 2016 result, and they improved their calibration of or systematic, and finally they removed some, they lower the upper limit with some factor, but not that much. So this is the latest result from the MW. Next is Lofer in Netherlands. So this is the latest upper limit from this paper, and this is the redshift 9.1, and here they applied the direction dependent calibration that I showed because of the ionospheric solutions. And this is the advanced technique for the calibration. And for the foreground removal, they use the Gaussian process regression. And this is the 141 hours of data using the Lofer, and this is the upper limit. Okay, now this is the HERA, Hydrogen Epoch of Reionization Array. So I am showing the result for different telescopes. So this is the located in Karoo Desert in South Africa, and this is designed for the epoch of reionization observation. What is the advantage is that they use some redundant calibration approach. So that I showed is the model incompleteness. If your calibration model is not accurate enough, the foreground will leak in your foreground free region, and it is difficult to measure the 21 centimeters. So this approach is that they have many antenna pair with same separation. So 1, 2, 3, 4. So the same separation but different antenna pair. Each pair will measure the same sky signal, but the instrumental properties are different. So based on this redundant calibration, this is one of the calibration techniques which you don't need any model for the sky. You can calibrate the signal using this measurement. So this redundant calibration approach is taken in this HERA observations, and they choose 3 observing fields which are free from the foreground. This is the galactic plane, and this is the 3 region of that sky which is free from the foreground, and they put some upper limit in their observation. So this is in 2021, and this is the best upper limit they got from this HERA observation. So if I compare all the observations that I showed, MW, Lofer, and HERA, this is the summary plot of all the power spectrum as a function of redshift. And here you can see that this is the 321 centimeter model with 3 parameters, and this is the best upper limit till now from the HERA observations. And all these are quite noise dominated. So what I can say is all the power spectrum are noise dominated because the signal is quite far away from this, but still this noise is much lower for the HERA compared to the other experiments. So recently HERA put another upper limit. The earlier was for 18 hours, 18 nights observation. Now this is the 94 nights of combined, and you can see that this is the earlier HERA observations, and this is the new one after 94 nights. So these upper limits are now quite sensitive. So if you, as I said, this is the noise dominated. If you combine more and more data to reduce the noise level, if unless it is not dominated by the other systematic, you can reduce the noise limit by putting more data. So this 94 nights, this is the best upper limit of the HERA. Okay. So this is the experiments that are already taking the data and putting some upper limits. But SK will give us SK will be able to enough sensitivity to measure the signal in actual real space, not in the Fourier space or the power spectrum. So this is the simulated sky of the SK and as simulated sky, and this is simulated SK observations on all the parameters for the SK are taken, and you can see this by comparing these two pairs that you can able to isolate the reionized region around the galaxies. So it can be possible to image the SK. So this website summarizes all the line intensity mapping experiments that are currently happening and which are the future experiments. So this is a quite nice documentation of that. Chime, HERA, Loafer, GMRT, MeerKAT, all these things, what are the interferometers currently operating. You can see a summary, what is the frequency band, what the line intensity they are trying to measure. So this is a good reference for the observation. Okay, so now I summarize all the global effort that 21 centimeter signal detection are happening and also people what are doing. Now I will talk about some of the our efforts that we are currently doing. So what the problem we choose that is that, so I said the foreground removal technique is the smoothness of the foreground as a function of frequency can be used to remove the foreground. That is the foreground removal technique. But what happens if there are some foregrounds at the outer part of this? So this is the central part of the sky region. It's a small part of the sky, and we are interested in the central part. But antenna is not, the antenna response is not exactly zero at the outer part. There are some non-negligible response function in the outside of the central region also. What will happen if any bright sources enough located in this region, it will create some oscillations. So although the foreground behaves smoothly as a function of frequency, but due to this outer region, due to some antenna non-negligible antenna response in the outer part, it will create some oscillation. So that is the problem, and it is very difficult to remove because the period and the amplitude is different depending on the source positions and also the source intensity. So we have to remove somehow. So that is the problem we choose, and we are working last few years to tackle this problem so that we can go to that level of the 21 centimeter signal. So what we developed is the tapered gated estimator. How it works? This is the image of the sky. So this is the antenna response of the sky, and this is the central part is most sensitive, but there are some non-negligible, and this is the null position. What we are trying to do? We are trying to multiply this image with a known window function, that is the Gaussian window function, so that whatever is outside, whatever signal is outside at the outer region, it will be suppressed. We will not interested in this part because this is create some oscillations which is difficult to remove. And what we effectively see is the central part only. So that is the main motivation for developing the estimator. But as I said, the interferometer measure in a Fourier domain, not in the actual domain. So this is the sky image. But in the Fourier domain, what we are doing, we are convolving this measurement with this Fourier transform of the window function. So this is the window function we want to apply, and in the Fourier plane, we are convolving this measurement with this Fourier transform. So what we will see, effectively this measurement, convolution measurement will suppress the contribution because this antenna response is multiplied with this window. That means whatever the sky signal is outside of an interstate region can be removed. And this is the three other advantage also. So this outer part mainly called the side lobe response. It will suppress the contribution, and it is a gridded estimator. For the large data, it is quite faster compared to the other. And also it removes the noise bias. So this is the three main features of the estimator that is incorporated, and it is used in the data that I will show to measure the 21 centimeter fluctuation. And this is the validation of one validation in one of the simulations. And you can see that tapered gated estimator will can able to recover the signal quite accurately as compared to the model signal. This is the next validation. So as I promised that it suppresses the contribution, so we have to validate that is it okay before going to the data. We have to show that it is yes, it is suppressed. So this is the whole sky, it's quite big sky simulation, and we are interested in the central part. So any sky contribution from the outer part will mainly dominated in the large L, basically the small scale. L is the Fourier conjugate of the sky coordinate, basically the theta. So this L is small so small scale structure light sources will contribute here. So this is the primary beam response. We are multiplying with this image so that whatever the outer part is there can be suppressed. Now this is the 4 defined window function we are applying in the image and we see the result. So this is the result. So when there is a no antenna, no window function applied, the green line, you can see this is, we are not able to recover the model in the large L region. So means there the contribution from the outer part is contributing here. Now when we reduce the window function, you can see that this can be suppressed. Whatever the outside can be suppressed and we can recover the model. So this is one of the validation. So now we have validated the estimator in the simulated data. Now it's time to apply in the real data. So we use 2 GMRT observations slightly off galactic plane. This is the 10 degree and minus 11 degree galactic latitude, and this is the result for the power spectrum. So we took the data in this is the coordinate system. We took the data from this sky position. We apply the estimator. We interest in the central part. Whatever outside is removed. Also, we remove the noise bias, and this is the result. So in this region. So this region is dominated by the unsubtracted. Because of the noise limit, we can't subtract, even in the central part, we can't subtract all the sources, all the unwanted sources. So that will contribute in the power spectrum or in the statistical estimate. But in some part where this is, we can able to recover the basically the galactic synchrotron emission. So this is the power law or the angular power spectrum of the galactic synchrotron. So this is one of the results of the application of the TG, tapered gauge estimator, in the GMRT data. So next we choose all sky. So TIFR GMRT sky survey is the all sky survey at 150 megahertz, and this is the blank region due to the declination limit of the GMRT. So this is the all sky image, and the left panel shows when there is a no foreground removal from the center part, and this is the right panel when we remove the central part, bright galaxies, and what we see is the galactic synchrotron emission, which is dominated maximum intensity at the galactic plane. So this is the one of the measurement of the galactic synchrotron using the TGE and the TAGSS survey in the statistical detection, mainly the power spectrum. So this is another result of the all sky survey in the GMRT observation. Sorry. Yeah. Okay. Okay. Next, we apply this TG to the another frequency band is 325. So all know PhD students, he was working in 18 those. So this is the image of the sky at this is the coordinate, and this is 325. And we have removed the bright point sources from the central part, and we apply the TG, and we are still able to recover some galactic synchrotron in the angular power spectrum. So this is just the result I am showing for the different measurement of the sky, different parts of the sky using the GMRT and TG application, and the statistical detection of the galactic synchrotron at different frequency band, at different location of the sky. Okay, so this is the 2-dimensional thing that I talked about. But now suppose we have the frequency measurement, so we are interested in the power spectrum pK. So that information is a 3-dimensional volume. So for that we need the frequency, the Fourier transform along the frequency also. But as I showed, if there are some RFI present, we have to, if any RFI is present along the frequency, we have to remove them. So there will be blank region, no data, because we have to remove the RFI thing. So if there is any RFI signal present and we have removed them, so when we go to the Fourier transform, it will create some oscillations because there is no data, just 0 in that frequency. What will happen? This plot shows the signal flag. When the signal is flagged, you will not able to recover the 21 centimeter signal in the higher delay. So this region is dominated by the foreground. This is the wedge region. So this is just plotting at particular k perpendicular as a function of k parallel, basically tau, which is the Fourier transform along the frequency. So the any baseline or any particular k perpendicular, the small k parallel region will be dominated by the foreground, and outside will be the noise and the signal. But if there is some channel flagging or any channel is missing, you will, this is the pattern. So you can't able to measure this signal. So somehow we have to overcome this issue. What we are doing now, we are measuring the multi-frequency angular power spectrum. So that now the TG is improved that I showed is for one frequency or combination of the just combine all the frequency. But here we are measuring the multi-frequency angular power spectrum. So what is this multi-frequency? It will measure the power spectrum. We have to measure the power spectrum as a function of frequency separation. So now, as I showed a single plot, now we have a same convolved visibility at different plane, and we can measure correlate this different channel or different. Then it will give the multi-frequency power spectrum, and this multi-frequency power spectrum can be used to measure the power spectrum. What is the advantages in the delta nu space? Suppose any channel is missing, I can get the combination from other frequency. For example, the channel separation 2, even if the channel 5 is missing, I can get the another combination from 4 and 6, sorry, or 6 or 8. So I can just completely ignore the channel what are flagged, and this is the result. Even if the 80% channels are flagged, we are able to recover the power spectrum and both multi-frequency angular power spectrum quite accurately from the simulation. So this is the result from the data using the multi-frequency and power spectrum. And here you can see that this is the two advantage. One is the multi-frequency, the channel flagging can be ignored. Even if the 80% channel are flagged, we can recover the power spectrum. All the and the basically the tapering function can be used to reduce the oscillations that I showed. Whatever the sources are in the outside, it will create some oscillations. But using the proper window selections or using a proper window, that oscillations can be suppressed so that the foreground can be removed. So Srijita will talk more about that. And this is the final power spectrum. Now there is still some noise. Basically, there are some noise from the different. Still, it is noise dominated. So to reduce that noise, we have introduced another, that is the cross polarization, RRLN. So the visibility measurement or the interferometer will give different polarization, RR and LL, and we can use this independent polarization measurement to reduce the systematics or reduce the noise. And here you can see the Asif will talk more about that. So after applying this cross polarization thing, you can see that this is the power spectrum. So this is the power spectrum that I showed from the Arnow's paper, and this is the showed from the earlier plot. And after using the cross polarization, you can see that the power spectrum can be improved quite accurately. Next, we have improved the tapered gated estimator quite more. What is planning to do that? What we are planning? The tapered gated estimator till now is for the tracking mode. We are concentrated a particular patch of the sky and moving the antennas throughout the whole night. But for another types of antenna is drip scan. The antenna is located in the ground and the sky is passing through. So this is totally different observations. That is called the drip scan observation. So this is the now the sky is fixed at this point, and the telescope is passing through at each second. It is measuring the different part of the sky. So this can be used. So basically, what we are doing here, we can combine, we can concentrate a such particular part of the sky, and we can combine all the measurement to reduce the noise. Or also we can concentrate in another part of the sky and we can combine. So what is the advantage is that by even if the telescope is looking a part of the sky, we can use a proper delay to change the phase center at multiple positions to reduce the cosmic variance. So that is the idea here. combine the signal from different parts of the sky to reduce the cosmic variance. So, this is the time, this is the blue line for the time. We can combine all of them to reduce the noise level that we are doing actually mostly. But this is the another technique to reduce the cosmic variance. We can point, so we can choose multiple pointing direction within the primary beam, where the antenna response more, and that can be used to reduce the noise level. And this is the plot. So Shumon is working on that, and this is the basically signal to noise ratio. You can see if we compare this 2 sigma, this is noise level. So the blue and the red, when you combine all these pointings, the signal to noise ratio increased a lot. So basically, this is the improving the signal to noise ratio using this new estimator, that is the tracking capability estimator. Okay, so this is the total thing that I wanted to talk. 21 centimeter is a promising tool to study the universe that we are listening from the beginning of the workshop. And different parts of the globe, people are working to measure for global signal, for interferometric measurement from the fluctuations, power spectrum, everything. And we have developed a novel estimator in this area to measure the power spectrum, both 2D angular power spectrum and 3D power spectrum. And there are some future telescopes, HERA and SK, will give us more constant result in the field. Yeah, so that's all. Thank you.
So I have a very naive question. So one of your cylindrical power spectrum plot, can you go to that slide?
Sure.
It is beginning. No, beginning. Yeah, this. So the red plot, I mean,
This one?
no, in the right panel, yeah, the red line, the red, for that plot, we have 2k parallel values. We have 2k perpendicular values for a single k parallel, or I mean, there is a multivariate function.
Which one?
The rate plot. Yeah, it will cut 2 points.
Oh, okay. This line and this line?
No. Not horizontal, vertical line at
Vertical line then?
this right side.
Okay, vertical line then?
Then that will cut 2k parallel values.
Huh, yeah. No, not all k parallel values. Oh, okay. This red line.
Yes, the red line only.
Okay. So that might happen because this is the 21 centimeter fluctuation. I think it's 10 times 20. That I have to take what is the factor. That is just to demonstrate that where the 21 centimeter is dominating. So if it is less the line, that means the 21 centimeter will be dominated beyond this region. If it is totally gone, that means no 21 centimeter is dominated by the foreground leakage. So that is just to show that 21 centimeter where it is dominating. This one, like that is the model actually. So it should not. If it is isotropic, that you can't expect. If it is anisotropic, then there should be some. Yeah.
Have to have just a single k parallel for a given k perpendicular or something. It's just the regions which will be affected by your incomplete source model.
Because this background is the incomplete source model. Now it is comparing this background, this color plot with where it matches that value. So that might be just total.
It's not a function or anything.
It's a boundary. Yeah. So that is basically depending on the model incompleteness. If it is incomplete more, then it might be. So just it is matching the background plot with this value. It will depend on the background or the model incomplete boundary. in model incompleteness. Yeah.
Yeah, thanks, Samir. This is the best talk I've heard on the status of 21 centimeter. This was really nice. Just maybe a related question: what is the current understanding of the contribution of unresolved point sources?
Okay. So unresolved point sources is basically that's why people are working on the avoidance technique, because unresolved, whatever it is unresolved due to the noise limit, we can't go beyond some noise level, and that will contribute actually, and we have to remove properly so that so below noise level we can't do anything. But if in the noise avoidance technique, in the avoidance technique, whatever the unresolved, it will contribute in this part. So that's why people are all the new foreground avoided technique. But unresolved will contribute, and how much we can avoid, how much we can subtract based on our noise measurement, we can remove. So that's why people are using both avoidance and removal technique. So we have to remove them or avoid them, but what we can do best based on the noise measurement, and people are using different techniques, but it is there. At some level it is there, yeah.
Maybe a related question. Basically, what I think Girish was trying to ask, at least what I feel, that in case of LOFA, they don't care about avoidance, right? They plan to remove everything, and their major issue was this unresolved point sources. So I think what Girish was trying to point at, that had they managed to make any progress so far, that's one. And then you showed a plot where MWA tried a hybrid technique, avoidance plus removal. So how did that fare compared to just avoidance or just removal?
Okay, let me go. So for the loafer technique, so they removed the, so they are for the remove you need a base model. So they are improving their model using different, for example, the direction dependent calibration, all these things. So they are working on that because they are not using the foreground avoided technique, but they're improving the model day by day. For example, this direction dependent calibration, and this is the base limit they got from the 140 hour observation. But still there are something, because if it is not, then we will detect the 21 centimeter. So that is not the case, but they are doing removing. Okay, so now this is the MWA. Yeah, so MWA they compared actually. There is a paper. They removal, avoidance, removal plus avoidance. So in the removal, so there are 3 techniques they compared in one paper, and they showed that for the MWA data, this hybrid technique is much effective compared to the 2. So that is they have, that's why they applied this. In
Did it improve the upper limit? Did it reduce the upper limit by what factor?
I forgot, but there's a paper by Daniel Jacob. So they compared these 3 techniques: only avoidance, only removal, hybrid. So that's why they use this hybrid approach now.
Okay, fine, thanks.
So another amateur question. I mean, why do we need nights for radio observation? Because in the loafer you have mentioned
night,
94 night.
Just to reduce the RFI. Yeah, that is the one thing. Yeah.
Okay.
Radio frequency, because in the daytime there are lots of mobile signals, all these things. RFI is much more.
But in night also there are mobile signals.
But there are others. So if you see the RFI pattern in the day and night, you can see that comparison. In the night it is much less compared to the daytime. Also it depends on the locations also. So night is always better compared to the daytime. So you can plot that I showed now, that RFI plot. Sorry if I see. Yeah, so this is the RFI plot. So if you see in the daytime or nighttime, this is for 2 locations, Karoo Desert and Marian. But if you plot the same thing in the day and night, you can see the difference. The night is always better.
So I have a very naive question. So can you measure global 21 centimeter signal with something like MWA?
That is they are doing now. That is only, so the global 21 centimeter signal will not, so not exactly zero, but at some distance you can measure using the interferometer also. So there is some pattern. So if you plot the global signal measurement as a function of two antennas, after when these two antennas is totally out, means the separation is more than the diameter, you will not measure the 21 centimeter signal. But there are some techniques, for example, lunar occultations, or they are using this to increase. There are some distance you can measure using the interferometer also. So that's why, yeah, that people are doing using the radio interferometer.
Hi. Hello. Yeah, this is. So, very nice question. I just want to ask you, there are lots of results from different telescopes. So, is it okay to rely on UGMRT observations? While yesterday's talk, somebody has shown the results based on simulation that with 1000 hours only, GMRT will not be able to give better results in comparison to other telescopes.
Okay, so this telescope thing depend on lots of systematics also. So after some time, so it's not like that if you add more and more data, it will always reduce. After some time, the systematic will dominate, which can't be improved using more data. So that there the systematic will dominate. So for that GMRT result, they used I think 1000 hours. So there is some systematic dominant. It is not only the noise dominated. Noise is not going down. So that's why your system should be improved enough so that it is noise dominated. If there is noise dominated, you can do something. But if it's systematic dominated, then you have to improve the systematic. So that's why the new experiments are coming. But the systematics is much better. You can't. You have to, for example, the HERA or the systematics is still that result are still noise dominated. That means adding more data, when it will hit that value, it is not going down. We can't do anything. So these results they are publishing, they are comparing with the noise, and it is still noise dominated. So that's why they are working more and more nights. For the GMRT result, that Peshiga that I showed, they use 1,000 hours also, and this is not reducing. So that's why, yeah. So UGMRT that we have to check because we have not that much now not that much data available for to reduce to go to that level. So that we have to check because for the earlier GMRT they did all these things.
Okay, thank you.